Welcome back, everyone, to our next lesson on energy. Today we're going to be talking about kinetic energy specifically and how we can transfer potential energy into kinetic energy and its relationship to work being done on an object. Because if you think about an object that is not moving, that is, let's consider a car that's just kind of sitting there, the velocity is 0. If we have a car coming behind, moving at some velocity, we'll call this 10 meters per second, it's going to strike this car in front. We'll call that 1. We'll call the one behind here 2. Car 2 is going to strike car 1, and since car 2 is moving, it contains a certain amount of kinetic energy. Therefore, it's moving with some kind of force. When 2 strikes 1 which is not moving, work has to be done on car number 1 as long as number 1 moves when 2 collides with it. And some of the kinetic energy that number 2 is moving with is going to be transferred into car number 1. And as long as that car moves some distance, we know that there's going to be work done on that vehicle as cart 2 provides a force to move cart 1 some distance. We know that this is due to the change in total energy. So the amount of kinetic energy that car 1 gains is equal to the work being done on it by number 2. So kinetic energy is the energy that an object is going to possess due to its motion. Due to its motion. So as long as we have an object, some type of matter that is in motion, it is going to contain some amount of kinetic energy, and we can actually calculate that. Up until now, we haven't really been able to, but we're going to look at an equation that we can use to help us calculate the kinetic energy of an object. So the moving object, as we looked at the scenario here to start the lesson, the moving object possesses energy, in this case cart number 2, due to its motion. So in that example, cart 2 has kinetic energy because it is moving. Cart 1 does not because it is not moving. It's at rest. There's no velocity. Now, the equation that we can use to calculate this is 1/2 mv squared. Where we measure the mass in units of kilograms, standard unit. Velocity or speed will be meters per second. And kinetic energy, being an energy value, will be measured in joules, or a capital J. And now Newton's cradle here is a good example of the conversion between kinetic and potential energy. In order to get the cradle going, we have to first supply some kind of energy to build potential within the system in order to get this thing moving. So we have to apply some initial energy by raising this ball here. I'll label that 1, raising it to some height. And at this point here, we're building potential energy because we've raised that ball from its point of rest further off the ground, and it has potential energy due to its higher position off of the ground. Once we release ball number 1, it's going to convert its potential energy due to gravity into kinetic energy. It's going to strike ball number 2, and we're going to have a transfer of that kinetic energy through 2 to 3 to 4 to 5, and we'll see this ball kind of come up and swing up to the top here. In theory, in a perfect world, this would go on forever, but it doesn't. Whatever potential energy that we give the first ball, the law of conservation of energy says that all of that should be transferred into 2, 3, 4, and 5, and we should have an equivalent amount of potential energy that 5 should gain on the other side. But it doesn't work like that. At least not in a perfect transition here from 1 to 5. We're going to lose some of this energy, not only due to friction between the balls, but also due to sound. Every time those balls hit each other, they make a sound, and some of that initial potential energy that we gave number 1 is going to be converted into sound. So by the time the potential energy transfers to kinetic at number 1, transfers through 2, 3, 4, and 5, the height that 5 rises over here is going to be less than the height that we released 1 at. So it's not really a loss of energy, but the transfer is not directly from one form of potential from number 1 to an equivalent amount of potential to number 5. It's lost a couple different ways along the way. I'm going to do a couple examples here with you guys. And I'll leave the third one here for us to do in class. So first one, how much kinetic energy is possessed by a 3.4 kilogram cart traveling at 2.9 meters per second? Now, just to kind of make note here, the question asks for kinetic energy. So we kind of want to direct our thoughts, initially here at least, to 1/2 mv squared. And to go through when we define here, just to make sure that we have enough, we have a 3.4 kilogram cart. So it's 3.4 kilograms. We'll fix that number. 3.4 kilograms, and we have a velocity here traveling at 2.9 meters per second. We don't know what the kinetic energy of the object is. So we can find that because we have the mass of the vehicle, and we know the speed that it's traveling at, 2.9 meters per second, and we're going to square that. It squares the velocity only. This gives us a value of 14.297 kilogram times a meter squared per second squared, or that's equivalent to 14 joules. So that cart traveling at that speed is able to do 14 joules worth of work on another object. Let's say it were to collide with something else. That's the maximum amount of work that that cart traveling at that speed will be able to do. For number 2 here, a 5 kilogram cart possesses 106 joules of kinetic energy. Determine the speed of the car. So we have 106 joules of kinetic energy. We want to determine the speed. We don't know that, but we do know the mass of the cart. So let's start there. We know the mass of the cart is 5.00 kilograms, and we know that it possesses 106 joules of energy. However, we do not know the speed at which that cart is traveling. So again, when you see kinetic energy, we're only using one equation for this, amongst other forms, especially when we're talking about work. We will kind of manipulate this a little bit. I'm going to plug this in as we have it. So we have 106 joules. That looks like 166, but it's not. It's 106. 106 joules equals 1/2 5 kilograms times our velocity squared. Now what this comes out to, if we were to reorganize this here, this will simplify down to our v squared equal to 2 times 106. And we divide that by the mass of the cart of 5 kilograms. This will give us a value of 42.4 joules per kilogram. And after rounded, we take the square root of that. We get a value here of 6.51 meters per second, and that is our velocity. We'll save the last example till class. Till then, have a great day.